Most welcome to 1203 of the Heidegger series. And we continue with chapter 4 of this marvelous book, Louder Than Words by Benjamin K. Bergen. While drinking something I can recommend, licorice tea. So we just finished the Grasposaurus, the most terrible device, and we went into looking further to the rest of the body, beyond the hand, so to speak. Next paragraph, aptly entitled The Rest of the Body. Thus far, we've only been looking at hand actions, but we know that there are specialized portions of the brain dedicated to controlling different body parts, from the tongue to the toes. Are these parts of the motor system, which we know come online when people are imagining moving their different body parts, also engaged during language understanding? To what extent is understanding language a whole body process? We know that the motor system is organized such that sets of neurons that drive very similar actions, like those responsible for executing different hand shapes, mutually inhibit each other. That is, when one is active, it sends a signal to suppress activation of the other. So that your muscles don't get competing, incompatible messages at the same time. It's critical for actions that use the same body parts to be mutually inhibitory, because you wouldn't want to try to do two things with the same body parts at the same time, like chewing and gargling. But if actions use different body parts, they need not compete with each other. Although holding a tray and putting in an earring ought not to be attempted simultaneously, there's no reason to keep yourself from trying to walk and chew gum at the same time. And that's despite what Uggla here in Sweden, the singer, told us. We can take advantage of these mutual inhibitions of actions that use the same body parts as a way to tap into how people employ their motor systems to understand language. Our brain won't allow us to perform two different actions at the same time using the same body parts. So if language evokes body part specific motor actions, motor simulation, then it should be hard for you to think about an action while simultaneously understanding language about another action that uses the same body parts. Here's how we tested this idea in my lab. First, we needed a way to get specific action circuitry fired up. We know from the mirror neuron research that we saw earlier that seeing someone perform an action activates the motor system. So we showed images of people performing actions to participants in order to activate their motor representations of those actions. Once these motor representations were active, we presented words describing different actions that use either the same body part or a different one. And we predicted that it would take people longer to process the action words when those words describe actions that use the same body parts as the action depicted in the image than when the actions used different parts. Suppose you see an image like figure 19. That's a man watching his clock. And then you are asked to decide if the following word describes it. Juggle. It should take you a relatively long time to decide that the picture does not depict juggling, because the two actions use the same body parts, arm and hand, in different ways. By contrast, you should take less time when you see the same picture and then are asked to decide whether the following word is a good description of the picture. Punch. This is because the word punch describes an action using the foot and leg, and therefore should not be in competition with the hand action the picture depicts. In a series of studies in English and Chinese, we found that it takes people longer to decide that the word is not a good description of an image when the action describes it. And the action the picture depicts use the same body part than when they use different body parts. We infer from this that the accessing the meaning of action words involves activating the specific parts of the motor system dedicated to controlling the relevant body parts. Another way you could test this would be to have people read sentences about actions that use different body parts. Turning a key as a hand action, kicking a chair is a foot action, for example, and then have them push a button with either the same body part or a different one. For these sentences, either their hand or foot. You would expect to see that if the actions that the sentences describe are different from the button pressing action, but use the same body part, then people should take longer to press the button. That is, if someone hears a sentence about turning a key and then has to push a button with their index finger, then these two actions should interfere with each other because they use the same body part in different ways. However, if they have to press a button with a foot after hearing the sentence about turning a key, there should be no interference, because we can turn a key and flex our foot at the very same time. Just like we can ride a stationary bike at the same time as we dial a phone. Fortunately, this study has been done. The results: hand sentences slowed responses using the hand, while foot senses slowed responses using the foot. Amazing. Let's suppose for a second that we take the preceding evidence at face value, that when people hear or read sentences about foot actions, they engage the parts of the motor system that control movement of the feet, and likewise that language about mouth actions engages the mouth controlling parts of the motor system, and so on. If this is the case, then the topology of the motor system should make a difference to processing. The motor strip is organized by body parts, such that the mouth controlling areas are lower down, and as you go up you find those regions that control the hands, and then the areas controlling the feet up at the top. We can use the fact that these different parts of the motor strip are in different places to make predictions about how long it should take people to process words describing actions using different body parts. This is a little tricky, so it requires some more explanation, but it's also very cool. As just mentioned in the motor strip, the neurons that control leg and foot actions are located at the top, with those responsible for hand and arm actions below them, and mouth controlling neurons are near to the bottom. But understanding a word about action naturally involves activating a number of parts of the brain, not just parts of the motor strip. Other neural structures involved include those in areas, for instance, that represent the pronunciation of the word, its spelling, and so on. These other parts of the brain are located closer to the bottom of the motor strip, representing mouth actions, than the top. You can take a look at one proposal for where the networks of neurons responsible for understanding leg-related, arm-related, and face-related action verbs should be in the brain. This is depicted in figure 21. What you see from these images is that the clusters of neurons used to understand leg-related words are substantially more spread out than those for arm or face-related words. This turns out to be pretty important, because when neurons become active and send signals to other neurons, The propagation of these signals takes time. The farther a neuron sends its signal, the longer it takes for the signal to get there. What does all this mean? Well, if understanding words about actions actually engages the parts of the motor strip that control those specific actions, then all other things being equal, people should take longer to recognize and understand leg-related verbs than arm-related verbs, which should in turn take longer than face-related verbs. Just because of the distances the neural signals have to travel to activate the entire networks that represent each of these types of words. Crazy though this prediction might seem, it turns out to be true. In several studies, German researchers have found that even when everything else is held equal, for instance the frequency and the length of the verbs, leg verbs are processed more slowly than hand verbs, which are processed more slowly than face verbs. The final piece of evidence that the whole body is involved in understanding language about action comes from the brain imaging. Several groups of researchers have looked at whether understanding language about actions measurably activates motor regions of the brain. One group had people simply read hand verbs like grasp, foot verbs like kick, or mouth verbs like bite. Another group gave people sentences like I grasp a knife, I bite an apple, or I kick a ball. Both used fMRI to determine whether the foot, mouth, and hand regions of the motor strip were selectively active during comprehension of the words or sentences. Sure enough, the results came out as shown in figure 23. The dark blobs, it's an image of the brain here. The dark blobs in this image represent those brain areas that were selectively active while people were processing mouth, hand, and foot sentences. There are interesting differences in activation throughout the brain, but of particular interest to us